If a transformer's nameplate lacks a class marking, you can ascertain its class by examining its temperature rise. This method relies on understanding the relationship between the transformer's temperature rise and its corresponding insulation class. Firstly, consult the transformer manufacturer's data. Access the manufacturer's website, catalogs, or technical documentation specific to the transformer model in question. This documentation usually includes the transformer's temperature rise information, which is typically expressed in degrees Celsius above the ambient temperature. The ambient temperature is the temperature of the air surrounding the transformer. Secondly, determine the class based on the temperature rise. Utilize a temperature rise table to correlate the transformer's temperature rise with its respective insulation class. Here's a commonly used table. A temperature rise of 65 degrees Celsius corresponds to class 105 degrees Celsius, which is class A. A temperature rise of 75 degrees Celsius corresponds to class 120 degrees Celsius, which is class B. A temperature rise of 85 degrees Celsius corresponds to class 130 degrees Celsius, which is class F. A temperature rise of 95 degrees Celsius corresponds to class 140 degrees Celsius, which is class H. A temperature rise of 105 degrees Celsius corresponds to class 155 degrees Celsius, which is class R. For instance, if the transformer's temperature rise is specified as 85 degrees Celsius, it's classified as a class F transformer. It's important to note that the temperature rise indicated on the transformer's nameplate is usually based on an ambient temperature of 40 degrees Celsius. If the actual ambient temperature is higher than 40 degrees Celsius, the transformer's temperature rise and insulation class may differ. If the manufacturer's data does not explicitly state the temperature rise, contacting the manufacturer directly for clarification is advisable. In summary, when a transformer's class is not explicitly marked, the temperature rise serves as a reliable indicator. By consulting manufacturer data and using the temperature rise table, the appropriate insulation class can be determined. Remember to consider the impact of ambient temperature on the transformer's overall thermal performance and consult the manufacturer if needed. Understanding transformer insulation classes is crucial for ensuring safe and reliable operation. Transformers are critical components in electrical power systems responsible for stepping up or stepping down voltage levels to meet the requirements of various applications. The insulation system within a transformer plays a vital role in preventing electrical breakdowns and ensuring the transformer's longevity. The insulation class of a transformer defines the maximum temperature that the insulation materials can withstand without significant degradation. This temperature rating is crucial for determining the transformer's suitability for specific operating conditions and its ability to handle thermal stresses. The temperature rise of a transformer refers to the increase in temperature of the transformer's windings and core above the ambient temperature when the transformer is operating at its rated load. This temperature rise is primarily caused by the losses within the transformer, including core losses due to hysteresis and eddy currents and winding losses due to the resistance of the conductors. The insulation class of a transformer is directly related to its temperature rise. Higher insulation classes are designed to withstand higher operating temperatures and temperature rises. Therefore, determining the insulation class of a transformer is essential for ensuring that it operates within its safe thermal limits. When the transformer nameplate lacks a specific class marking, the temperature rise becomes a key indicator of the insulation class. The temperature rise is typically specified in degrees Celsius and represents the maximum allowable temperature increase above the ambient temperature. To determine the insulation class based on the temperature rise, you can refer to industry standards and guidelines that provide a correlation between temperature rise and insulation class. The table mentioned earlier provides a common reference for relating temperature rise to insulation class. For example, a transformer with a temperature rise of 85 degrees Celsius is typically classified as Class F, indicating that its insulation system can withstand a maximum temperature of 130 degrees Celsius. It's crucial to understand that the ambient temperature plays a significant role in determining the actual operating temperature of the transformer. The ambient temperature is the temperature of the air surrounding the transformer and can vary depending on the installation environment. The temperature rise specified on the transformer nameplate is typically based on a standard ambient temperature of 40 degrees Celsius. If the actual ambient temperature is higher than 40 degrees Celsius, the transformer's operating temperature will be higher, and its insulation system may be subjected to higher thermal stresses. In such cases, it's essential to direct the transformer's load capacity or take other measures to ensure that the insulation system remains within its safe operating limits. If the manufacturer's data does not specify the temperature rise, it's advisable to contact the manufacturer directly for clarification. The manufacturer can provide the necessary information and guidance to ensure that the transformer is operated within its specified thermal limits. In addition to the temperature rise and insulation class, other factors can affect the transformer's thermal performance, including ventilation, cooling methods, and load characteristics. Proper ventilation is essential for dissipating heat generated by the transformer. Adequate airflow around the transformer helps to remove heat and maintain a lower operating temperature. Cooling methods such as forced air cooling or oil cooling can further enhance the transformer's thermal performance. Forced air cooling involves using fans to circulate air around the transformer, while oil cooling involves immersing the transformer in oil to dissipate heat more effectively. The load characteristics of the transformer can also affect its thermal performance. Overloading the transformer can lead to excessive temperature rise and potential damage to the insulation system. It's important to operate the transformer within its rated load capacity to ensure safe and reliable operation. In summary, when a transformer lacks a specific class marking, the temperature rise serves as a valuable indicator of its insulation class. By consulting manufacturer data, using temperature rise tables, and considering the impact of ambient temperature, you can determine the appropriate insulation class and ensure that the transformer operates within its safe thermal limits. Proper ventilation, cooling methods, and load management are also crucial for maintaining the transformer's thermal performance and extending its lifespan. Understanding transformer insulation classes is essential for electrical engineers, technicians, and anyone involved in the installation, operation, and maintenance of electrical power systems. By adhering to industry standards and guidelines, you can ensure the safe and reliable operation of transformers and prevent potential failures due to thermal stresses. The National Electrical Code, or NEC, provides guidelines for the installation and operation of transformers, including requirements for ventilation, clearances, and overcurrent protection. NEC Section 450.21b Exception 2 addresses the installation of dry-type transformers in non-fire-rated rooms. This exception allows for the installation of transformers with specific insulation classes in such rooms provided certain conditions are met. Specifically, the transformer must be Class 155 or higher. This requirement ensures that the transformer's insulation system can withstand the potential fire hazards associated with the non-fire rated room. When installing a transformer in accordance with NEC Section 450.21b Exception 2, it's crucial to verify that the transformer meets the insulation class requirements. If the transformer nameplate does not explicitly state the insulation class, the temperature rise method described earlier can be used to determine the class. By consulting manufacturer data and using the temperature rise table, you can determine whether the transformer meets the Class 155 or higher requirement. In addition to the insulation class requirements, NEC Section 450 provides guidelines for other aspects of transformer installation, including ventilation, clearances, and overcurrent protection. Adequate ventilation is essential for dissipating heat generated by the transformer and preventing overheating. Clearances must be maintained around the transformer to allow for proper airflow and access for maintenance. Overcurrent protection devices, such as fuses or circuit breakers, must be installed to protect the transformer from overload and short-circuit conditions. Adhering to the NEC guidelines is essential for ensuring a safe and reliable operation of transformers and preventing potential hazards. In addition to the NEC, other industry standards and guidelines provide valuable information on transformer installation, operation, and maintenance. The Institute of Electrical and Electronics Engineers, or IEE, publishes various standards related to transformers, including standards for testing, performance, and safety. Consulting these standards can provide further insights into best practices for transformer management. Understanding transformer installation classes, temperature rise, and applicable codes and standards is crucial for ensuring the safe and reliable operation of electrical power systems. By following industry best practices and adhering to code requirements, you can prevent potential failures, extend the lifespan of transformers, and protect personnel and equipment from electrical hazards. The information provided here is intended for general guidance only and should not be considered a substitute for professional engineering advice. Always consult with qualified electrical engineers and adhere to applicable codes and standards when working with transformers and electrical power systems. Transformers play a vital role in modern electrical grids, enabling the efficient transmission and distribution of electrical power. Understanding their characteristics and proper installation and maintenance practices is essential for ensuring a reliable and safe power supply. Transformers come in various types and sizes, each designed for specific applications. Dry-type transformers, as mentioned in the question, are commonly used in indoor applications where oil-filled transformers are not suitable due to fire hazards. Dry-type transformers rely on air as the primary cooling medium and do not contain flammable liquids. This makes them a safer option for indoor installations. However, dry-type transformers typically have lower overload capacity compared to oil-filled transformers and require proper ventilation to prevent overheating. The kVA rating of a transformer indicates its apparent power capacity, which is the product of voltage and current. A 150 kVA transformer, as mentioned in the question, can supply 150 kVA of apparent power. The actual power that the transformer can deliver depends on the power factor of the load. The power factor is a measure of how effectively the electrical power is being used. A power factor of 1 indicates that the voltage and current are in phase and all the power is being used effectively. A power factor less than 1 indicates that the voltage and current are out of phase and some of the power is being wasted. Transformers are designed to operate at a specific voltage and frequency. Operating a transformer outside its rated voltage or frequency can lead to reduced performance and potential damage. It's important to ensure that the transformer is connected to the correct voltage source and that the frequency of the power supply matches the transformer's design specifications. Transformers are also subject to various types of losses, including core losses and winding losses. Core losses are caused by hysteresis and eddy currents in the transformer core. Winding losses are caused by the resistance of the conductors in the transformer windings. These losses result in heat generation and reduce the overall efficiency of the transformer. Transformer efficiency is a measure of how effectively the transformer converts electrical power from one voltage level to another. High-efficiency transformers can significantly reduce energy consumption and operating costs. Regular maintenance is essential for ensuring the long-term reliability and performance of transformers. Maintenance activities include visual inspections, insulation resistance testing, and oil analysis. Visual inspections can help identify any signs of damage or deterioration, such as cracks, leaks, or corrosion. Insulation resistance testing can assess the condition of the transformer's insulation system. Oil analysis can detect any contaminants or degradation products in the transformer oil. By performing regular maintenance, you can identify potential problems early and take corrective action before they lead to catastrophic failures. In conclusion, transformers are critical components in electrical power systems, and understanding their characteristics, installation requirements, and maintenance practices is essential for ensuring a reliable and safe power supply. By adhering to industry standards, following code requirements, and performing regular maintenance, you can extend the lifespan of transformers, prevent potential failures, and protect personnel and equipment from electrical hazards. Remember to consult with qualified electrical engineers and adhere to applicable codes and standards when working with transformers and electrical power systems. The information provided here is intended for general guidance only and should not be considered a substitute for professional engineering advice. Always prioritize safety and follow established procedures when working with electrical equipment.